Thank you everyone for watching today's webinar. This is a recording from a live webinar that was presented on May 9th, 2013. My name is Brad Elkins. I'm a technical sales representative with EOS Remediation, and I'll be the moderator for today's webinar. The title of today's presentation is Anaerobic Bioremediation System Optimization, and our presenter is Dr. Stephen Richardson of Solutions IES. Dr. Richardson is a professional engineer with Solutions IES and received his Ph.D. from the University of North Carolina in Chapel Hill. And without further ado, I'll turn it over to Dr. Stephen Richardson.
Thanks, Brad. I appreciate the invite to give this webinar. Usually this is a Bob Borden webinar, but I guess it's my turn to be in the hot seat, so I'm actually very happy to be here. And so the major topic, or the topic of this webinar, is anaerobic, again, bioremediation system optimization. It's a mouthful, but what we're really getting at is ways that you can improve your emulsified oil design based on the key design parameters that we're looking at. And this work really reflects a collaboration between Solutions IES and North Carolina State University through an ESTCP funded project that was ER0626. So I'll be speaking mainly about that design tool today. The webinar outline is as follows. We're going to briefly discuss emulsified oil process. I recommend for those that are new to the emulsified oil arena, or at least in the design area, to look at some of the webinars that EOS puts on annually. There's one on Bioremediation 101. There's another that is a managing pH of aquifers, and there's another on substrate selection. And so those will give you a more detailed overview of the emulsified oil process, much more detailed than I'll go through today. Again, the focus is going to be this ESTCP funded design tool that is freely available to everyone out there. You can go on the ESTCP website, or it's available on the EOS website as well. I'm going to be looking at how to improve treatment, how to design an injection system, how to estimate reinjection frequency, how well, basically looking at a variety of different well installation methods, and then we'll look at cost sensitivity analysis. This is not the order in which I'll be doing it. Basically these parameters are sort of intertwined, and so I'll be discussing all of these, but I will touch upon them all just in a different order. So briefly, the emulsified oil process, what you do is you install temporary or permanent injection points. Typically your temporary wells are 1 inch in diameter. Your permanent wells are conventionally drilled, can be 2 inches in diameter up to 4 inches in diameter, I've seen. And you arrange them in a grid or a barrier configuration depending on your site conditions and your project goals. You will then prepare and inject that emulsion, and by prepare what we mean is you would typically dilute that substrate. EOS, I believe, recommends anywhere from 1 to 4 to 1 to 20 with potable water. And then you'd follow that injection up with chase water to distribute the emulsion through the through the treatment zone. What happens in subsurface is that the oil droplets will eventually stick to the sediment surfaces, and they will ferment over time, releasing hydrogen and acetate, which are the drivers for the reductive dechlorination process for chlorinated solvents. The goal here, and the goal of this design tool that I'll be speaking about, is to achieve better contact, which translates directly to better treatment. But before I get into the nuts and bolts of this model, I thought I'd bring up some of the preliminary work that was done by Bob Borden's group at NC State, where they were looking at doing numerical model simulations to evaluate effect of significant design parameters for emulsified oil treatment systems. Those design parameters evaluated include the oil mass, the fluid volume, and that includes both your oil plus your chase water. Your well spacing, that's an important parameter. The closer you put your wells, the better your distribution, but your costs will go up. Injection timing is another one. Do you inject one well at a time? Do you inject all your wells at once? Do you manifold them up, or do you do a sequential injection? Perhaps inject well 1 and 3 and 5, and then do well 2 and 4 following that. So there are these design parameters will directly affect your cost at the end of the project. Performance criteria. So in order to make sense of the results of the model simulation, the Borden group had to come up with some performance criteria, and what these are is soil within the target treatment zone is contacted if the final oil content is greater than 5% of your maximum oil retention. And so that's a mouthful of a sentence, but what that means is that for every unit volume of aquifer material, there is a maximum oil retention that it can receive, or basically it serves as a reservoir. For this system, what they're hoping to achieve is that you get 5% greater than the maximum oil retention, and what that allows is that there will be distribution of that oil beyond that treatment volume. So it sticks to all the sites. Once the sites are all filled up, then it moves on to the next unit volume. And that is the volume contact efficiency parameter, which I'll be discussing later in the slides. Water flowing through a barrier is contacted if water contacts soil with greater than 5% of the maximum oil retention. Again, it's a very similar statement. What this relates to is a flow contact efficiency, and again, I will be discussing that later in the presentation. So this is what one of the simulations looked like. What they used was ModFlow RT 3D, and they assumed a 3D heterogeneous aquifer. And you can see in the permeability distribution, that's the graph 1, that there's a variety of different K values that you're looking at, different lenses. The darker red is higher K, and the whiter or light pink is lower K zones. And that has a direct impact on your oil retention or your oil distribution from the wells. So those vertical lines that come across those graphs are your actual injection wells. So you can see that the final oil retention graph at the bottom, or profile, shows that you get some connectivity between the wells, but there are areas where there is no contact, and so therefore there is no treatment. And so what the goal here is that with this design tool, your hope is that you can better understand your system and come up with educated decisions on how to improve the distribution between wells and to improve your treatment overall. So that brings me to this slide. The question is, how do you improve treatment? And as I mentioned, that basically this is a contact sport. You need to have all of your ingredients that can basically catalyze the reductive dechlorination reaction at one location at one time. And so what you need is your electron donor, you need your electron acceptor, and you need your bacteria all in one location. So how do you improve this contact? Well, the one thing you can control is where your oil goes. You can control how much you add. If you add more, you tend to get better distribution and better connectivity between wells. Of course, that costs more money. You can inject more water to distribute that oil. That is an option that can be done, but that increases your labor costs. That's more water to inject, which means more guys out on the field site dealing with pumps. And you can install more closely spaced wells. Again, I've sort of touched upon that. The closer your wells are together, the more materials, the more labor. So again, that increases your costs. And so the question is then, which do I focus on? Do you do all? Is there one that's more important than the other? And so that's where the ESTCP project ER0626, as I mentioned before, which is titled Development of a Design Tool for Planning Aqueous Amendment Injection Systems. This is where that design tool comes in. It's going to help you decide where to invest the majority of your funds for the project, and to figure out ways to optimize the system. So like any model, this will have input parameters, and this should be no surprise to all of you out there that obviously you got to put in your site data. That's one. Aquifer characteristics, contaminant concentrations, your biochemical data. In terms of biochemical data, that's your pH, your ORP, but it also includes your non-target electron acceptors, and I mean like the sulfates. These can play major roles in the amount of oil that you require and the amount of hydrogen that you can produce. You need to consider your costs. What are your fixed costs, your drilling costs, your substrate costs, your labor for injection. All of those play a part and are affected by the way you design your system. In terms of design information, you have treatment zone dimensions, contact time. Contact time in particular is a key parameter, particularly for treatment efficiency. Your design life and your scaling factors. And scaling factors are dimensionless factors that are used in the model basically to compare between simulations. But it represents the amount of oil, so the mass of oil or the volume of oil per unit of aquifer material that is there. And we'll be talking about those in some slides ahead. And then lastly, your output. You're trying to achieve an optimal contact efficiency. You're trying to understand your capital costs and, more importantly, your life cycle costs for your system. And on the right there is a flow chart that you would see when you download the Emulsified Oil Design Tool. You'll see this flow chart as one of in the user guide, and it basically will walk you through some of the process that's involved in going from your input parameters to your output. So injection system layout. There are two configurations that you can consider. There is a source area configuration, which is a grid of injection wells, and then there is the barrier. Looking at the source area, typically that requires more wells. You're basically putting wells or gridding up your source area that you have. So if you have a larger source area, it's obviously going to require more wells, more substrate. This treatment's more effective, or most effective, in the high K zones. When you're looking at barriers, this is a row of injection wells that is designed to intercept the plume, so you're not actually injecting directly into the source area. What you're doing is the contaminant is dissolving into the aqueous phase and being transported down gradient, where it is intercepted by this treatment zone. So this is essentially a permeable reactive barrier. Typically it offers lower costs because you require fewer wells, and less substrate is required as well. So there are key treatment zone dimensions or parameters that need to be input into the design tool. One of those is the width of your treatment area or your treatment design. The width is always, in this case, perpendicular to groundwater flow, and so this is a little confusing because when we talk about barriers, we say, oh, the length of the barrier is going to be 50 feet or 100 feet. Well, that is actually the width in the design tool. The width is perpendicular to the direction of groundwater flow. And when you look at your length, this is parallel to groundwater flow, so your source length is just, again, the other parameter to the width for source, so your length times your width. And in barriers, it's really, I've heard it termed as your thickness of your barrier, but in this case, for the design tool, is termed the length. And that's really going to be dependent on the contact time. If you have a very fast-moving aquifer in terms of groundwater flow, you may need to increase the length of your barrier to achieve the contact time that you need to get the treatment that you're looking for. And then there's the vertical thickness. This is Z in the schematic over on the right, and essentially that is your well interval that you're injecting into. What you need to consider, though, is if you have a variety of different layers, you have high K, low K zones within that well interval, you should really consider the effective thickness, that being what is the length associated with the formation where you can actually get where the emulsified oil will likely travel, so the path of least resistance. And so that's something you can play with in the design tool as well. Again, you'll arrange your wells in rows perpendicular to groundwater flow, wider spacing between rows to allow for down gradient drift. And so that's similar to the idea of a barrier. You space between your rows greater, and suddenly you end up with several barriers that are now intersecting either your source zone or your down gradient plume. Just for some definition, SW is your spacing of wells within a row, and SR are spacing of the rows. This design tool has a ratio of SR to SW between 1 to 1 and 2 to 1. And I'll show you the difference in the output when you change these parameters later on. And again, this design tool will also help you select the optimum SW, so the spacing of wells within a row, and that is a key parameter. Other parameters to consider are your fluid volume and your oil requirement. And so it's a simple formula. This is your base treatment volume area, base treatment volume, or your BTV, your effective porosity, which is NE, it's dimensionless. And then here comes this volume scaling factor that I mentioned before. And your volume scaling factor is the ratio of fluid, and that's your emulsified oil plus water injected per well to the pore volume within a base treatment volume around each well. So essentially it is the emulsified oil and water that's injected within the pore volume of the treatment that you're looking for. So the BTV in this case is essentially a cylinder. It's your radius of influence and then your Z, or your thickness. And it is how much oil you want to have within that BTV. And typically that ranges from 0.2 to 0.6 for area treatment. When you go to oil requirements, again, this is a similar formula. Maximum oil retention is a key parameter, which is pounds of oil per pound of soil. Your soil bulk density, pounds per cubic feet. And then this is a mass scaling factor. So what's different is this is the actual ratio of the mass of oil that's injected per well to the oil required to fill all the attachment sites within the BTV. And I'll explain why these are different later on. But typically it's very similar that you could input here this unit factor between 0.2 and 0.6. Furthermore, oil retention is a function of several parameters, and these need to be taken into consideration as part of your design. One of them is droplet size. Another is the capacity of the soil to hold oil droplets. It's basically the absorptive capacity of your soil material, the type of surfactant that is in your substrate, and then the surface charge of your sediments and droplets play a role in how far you can distribute this material and how long it will stick to the sediment material. So your droplet size, oil droplets should be smaller than the sediment pores for easy transport. Most substrates have near micron droplet sizes, and so they easily pass through most pores. Pore throats of 30 microns are pretty typical. As you get into the clays and tighter material, it can get smaller, but generally that's a fair estimate. Capacity of the soil to hold oil droplets. Silts and clays have more charged sites, and therefore will hold more oil. Your surfactant type will matter. The non-ionics will typically not absorb as much as the ionic surfactants. For example, lecithin will absorb significantly more than some of the other surfactants that are out there. And then surface charge, most clays have a net negative charge. Negatively charged droplets will have lower retention, so they'll pass through. So this gives you an idea of what the maximum oil retention number looks like. In the lab, this is some lab column study work that was done at NC State, and you can see the first 3 rows are synthetically blended material. You've got a blended sand with a variety of different silt and clay. and a column was run, and you can see what the maximum retention values. The main take-home message in this slide really is that as you increase your clay content, you're going to tend to see greater maximum retentions in the soil. So here's the volume contact efficiency that I mentioned before, and this is the main performance metric for area treatment. So on the X and Y-axis, you have again the volume scaling factor and your mass scaling factor. And your volume scaling factor again is the volume of soil, or excuse me, the volume of oil and water per unit volume of aquifer material, or a pore volume of aquifer material. The mass scaling factor is the mass of material that you can get into the subsurface per unit volume of material. So it's slightly different. So what it means is that you can have a lot of oil going in but very little volume, or you could have maybe a lot of oil going in and a lot of volume. So that would include you'd have a lot of chase water or dilution water as well. What this graph shows, this is a regression surface graph, and it's basically showing you the effect of volume scaling factor and your mass scaling factor, again the volume and the mass of oil that you're adding to the subsurface, and how that affects the contact efficiency, and that's defined as your volume contact efficiency, or EV. In this case, this is where you set your row spacing and your well spacing equivalent, so it's essentially a grid. And what you can see here is that you get very a very quick response, I guess, or a more significant response initially as you increase the amount and volume of oil that you add. You get up to about a 25% contact efficiency initially. You can see that the curve levels out over time, and so there is basically diminishing returns on this, meaning you don't really need to be adding massive amounts of oil. And that's why we recommended in the previous slide to have volume and mass scaling factors between 0.2 and 0.6, which is where you get the best bang for your buck. Now when you change the row spacing to be 2 times the well spacing, you can see that the contact efficiency overall dropped slightly. So it went from around 75 with the highest mass and volume scaling factors, and it dropped down to just above 50. And so that gives you an idea as you space your wells further and further apart, you're getting you get worse distribution, and of course your contact efficiency then drops as well. So this is again, I mentioned that the performance metrics are a little different for a barrier, that is flow contact efficiency. And flow contact efficiency really is the fraction of groundwater flow through the barrier that comes in contact with aquifer material, where the oil retention is greater than that critical oil retention that's defined. And so that again is another mouthful, but if you go back to our original slides and of our performance criteria where it's 5% greater than the maximum oil retention, that's what it means. It is a groundwater flow derived contact efficiency rather than a volume, which would be again the oil and water that is being injected. And so this graph looks a little different. You can see that again you get a very steep curve initially as you increase your mass and volume scaling factors, and then it levels off, so you get a diminishing return effect. But the overall contact efficiency is higher. And the reason that the flow contact efficiency may be greater than the volume contact efficiency is because oil preferentially flows through and contacts high K zones. So since these high K zones also transport most of the water, your flow contact efficiency ends up being greater than your volume contact efficiency. Now contact time, barrier contact time. This is another important parameter. Again, the longer your oil and contaminants are in contact, the better chance that you have for treatment. So you typically want to provide between 60 and 120 days for satisfactory chlorinated solvent removal. You may need longer contact time, and again this comes with non-target electron acceptors such as sulfate, you would need to add more oil to basically deal with that non-target loading. You have unknown high K layers that could cause short-circuiting through the oil-treated zones, so your oil is moving away faster than you would anticipate. You have high contaminant concentration, so you have a huge electron acceptor demand, so you need to counteract that with a large hydrogen demand or hydrogen supply. And then high removal efficiency required. So if you want your removal efficiency or your contact efficiency to be much higher, then you need to consider greater contact time. This translates to, again, a barrier. If you look at a barrier, that would really come down to the thickness again, or in the case of the model, the length of your barrier. So the longer your barrier is, the more oil that water is passing through will come in contact with. So you get more collisions or more chance for oil and contaminant to be in contact with each other. And that's really defined by this very simple equation here. X equals your contact time times your groundwater velocity. The greater your groundwater velocity is the greater that you're going to want your X variable to be. So another important question, or one that comes up often, I believe Brad gets this question a fair amount, is when do we re-inject? And there really is no hard and fast answer, and it's sort of a frustrating answer, but it's true. But we can give you some rule of thumbs that will help guide you towards your next re-injection. If you're using a soluble substrate system like lactate or molasses, typically these get burned up fairly quickly. They ferment fairly quickly, produce a lot of hydrogen initially, and then not a whole lot later on. And so you're going to have no choice but to re-inject a lot sooner than you may want to. And in order to maintain longevity, you would obviously have to maintain a lot of TOC. And so that's why these re-injections are required. You need to maintain anywhere from 50 to 100 milligrams per liter TOC to just keep that system going. Some emulsified oil systems, again, the oil droplets attach to the solid phase, and typically when you're talking about TOC, you're talking the majority of it is sorbed to the aquifer material. The aqueous TOC can be a good metric for figuring out when you require re-injection. Aqueous TOC of less than 20 milligrams per liter can still give you very good treatment. And you can see here in the lab column experiment that was done in Dr. Borden's lab, you can see that first thing you want to make sure is that you're still producing methane. That gives you your first indication that you have fermentation occurring. The second thing you can look at, obviously, if you drop down to the third graph, is your TOC, and you would have, as you would expect, a huge spike in TOC after your injection, and it would rapidly drop off as it's been distributed away for your injection well, and then you would end up with some sort of steady state TOC concentration. And in this graph, that ranges from 20 to 40 milligrams per liter. And so if you now hop to the middle graph, you can see that PCE and TCE drop off fairly quickly after your initial spike of TOC, and you're still able to maintain a very consistent DCE production over 400 days at a TOC between 20 and 40 milligrams per liter. So it's pretty solid evidence that I've seen rules of thumb that are greater for this, but in fact what we've seen is that your TOC can be actually fairly low. The key there is to actually just watch the trend. If you see that your steady state or your consistent concentration of TOC starts to drop off after a certain amount of time, that may be time to do a re-injection. And I've got a example here of that. This is an ESTCP demonstration project focusing on perchlorate, but the story is very similar. This was a barrier set up. On the y-axis is perchlorate concentration on a log scale, and then on the x-axis is your days since EOS injection. You have an upgradient, a series of upgradient wells, 25 feet upgradient, that's in pink, and then your injection wells are in blue, and your 10 feet down gradient and 20 feet down gradient are orange and light blue respectively. And what you'll notice there, that the takeaway message here is that 10 feet down gradient, you basically have dealt with the majority of your perchlorate or your contaminant, and it's basically gone. 20 feet down gradient, you have a bit of a lag, but you're still seeing some dramatic removal. Up gradient, just to show that what the initial concentrations are, and that there isn't any dispersion or any change or any dilution that's occurring because of that treatment. You can see that the 25 feet up gradient is basically constant. There is some rebound in your injection wells, and you tend to see that, but if you're doing a barrier system, basically your down gradient wells are there to deal with that. What I wanted to relate that graph to is your total organic carbon. So this goes again back to when do you re-inject. And so after initial spike, you get a really high TOC concentration, upwards in the thousands or close to 1,000. And then over time, if you follow that blue line, you can see you get this sort of steady state, or this steadying out of your TOC concentration. And then after about 800 days, in this case, we started to see a drop. And it's really at that point where you might want to consider reinjection, that your substrate may be exhausted. So now finally getting to the design tool, there's not a whole lot to go through here. It's fairly self-explanatory, but I do want to sort of introduce you to what it looks like and what are some of the buttons that you can push. But this is the ESTCP funded design tool that Solutions and North Carolina State University put together. It's an Excel-based spreadsheet, and it has 4 basic sections that you can look at. That's site data, installation and injection, barrier treatment, and area treatment. Basically, you click on those buttons to navigate between each of those sections. The first that you'll deal with is your Aquifer Description. It's pretty self-explanatory. They use some common information, your depth to water table, top to the injection zone, bottom of the injection zone, so that's your screened interval, what's your porosity, what's your effective porosity, and then it will calculate a seepage velocity for you. So anything that's in red is required to be entered. Anything that is not and still white, you do not have to fill out, and anything that is gray is actually calculated for you. And you always have a chance to get out. You can go back to the previous page. You can return your table of contents, so you can see that there are these buttons down here, so you can always figure out where you want to be next. Again, this is also an input parameter, your contaminant and biogeochemical characterization. You're going to need to provide your aqueous phase, PC, TC, concentrations, all the daughter products. You also have the option to add in other contaminants that you're interested in those blank spaces there as well. In addition, your biogeochemical data is key. It's important to know what the DO is, what the ORP is, to see if it's a suitable site for anaerobic bioremediation. And then also, more importantly, really are your background electron acceptors. How much oxygen, nitrate, sulfate do you have to deal with and reduce before you can actually start dealing with your contaminant. Your well installation method, this goes again back to, you have 2 options. In fact, you have 3 options I didn't mention in the first slide. You can also inject directly through your direct push rods. But I think this design tool really focuses mainly on the temporary or permanent wells that are installed using a direct push equipment. And it's going to give you a cost. It's going to give you a total fixed cost, dollars per injection point, injection rate, and injection cost per day. So you can choose how you want to proceed. You can change it, take a look, and see how it changes. So there's a lot of flexibility in this model. The other point to make here is that multiple wells are manifolded together for emulsion injection. That's a typical thing to do. It's not often that you see people inject just one well at a time. Simply, it gives you an option to save on labor costs. The question is, how many do you manifold together, and in what order? And so that's typically what people who look at are most interested in. And then lastly is your barrier design information. As I mentioned, we need to know your length, width, and your thickness of your treatment area, of your barrier or your area, your source area that you're interested in, your targeted carbon released, your design life, and your mass, volume, and substrate scaling factors. And again, you can estimate those, you can play with them, but the earlier slides should help you better understand what those factors mean. Again, it's the amount of oil that you're adding per unit volume, and so it's anywhere from 0.2 to 0.6 is a good number to type in. And your model then calculates your expected contact efficiency, and you can consider whether that is a good efficiency for your needs or not, and then adjust your design accordingly. And this is what your printout will look like. It summarizes everything you entered, and then basically your total life cycle costs, your costs for future injection events, your costs for initial installation and injection, and basically summarizes everything that you need, and then gives you an option again to go back and make changes, and you can keep printing these out so you can make some comparisons. Just to give briefly touch upon cost, and then we'll end the webinar. There are some effects of contact efficiency on cost. Typically for barriers, the flow contact efficiency really doesn't have that much of an impact on cost when you're looking for anything less than 85%. So you can see in the graph on the right at the top that everything is generally pretty stable until you start reaching beyond 85%. And this is basically a variety of different setups. If you had deep groundwater, you had high groundwater velocity. If you had thin interval, you had narrow plume or wide plume or high sulfate. So there's a bunch of options there that were looked at that we typically see, and in summary, basically you don't see a lot of impact until you get beyond 85%. With the area treatment, though, you tend to see a linear increase in your contact efficiency, and again, mainly this all comes down to your groundwater is what is transporting in the flow contact efficiency. What you're looking at when it's for your barriers is the transporting of the contaminants through the barrier that is giving you your efficiency. And so in general, what you'll see is you won't see a whole lot of change until you aim for higher contact efficiencies, because with a barrier you generally are able to achieve pretty stable efficiencies. So this is a simplified model to estimate your cleanup time. Again, another question that people ask: how long do I keep running this? And there again, there's no good answer. If you also have back diffusion from untreated low K zones, that puts a kink in the plans. What typically will happen is you have high K zones, you treat them very well, and then once your substrate's depleted, you tend to see a rebound. And this happens less on the biological side and more on the sort of chemical oxidant side, where you'd see that quicker rebound after a year. With the oils, there tends to be greater retention, so you would deal with some of that back diffusion, but it essentially does complicate things and puts a little bit of uncertainty into your cleanup time. Your time to get 95% mass degradation, we got a variety of different R factors here, your retardation factors, and then on x-axis you have your volume contact efficiency, and you can see that as you increase your volume contact efficiency, you are going to reduce the time that it takes to get that cleanup time that you're looking for. Now, the effect of error in estimating your your oil retention, your maximum oil retention. So this is a key parameter in the design, and it does affect, and you probably notice as you play around with it that it does change the output pretty substantially. But you can get a rough estimate for ORM by picking values off a table. But the problem there is that if you overestimate, you can increase your cost by over thousands, hundreds of thousands of dollars. If you underestimate, you don't get the contact efficiency that you want. So we highly recommend that you measure your ORM whenever possible, and you can do that. You can send samples to Microbial Insights, I believe is one vendor that will do this for you, and it's a simple small column test that you run the oil through the column and you see how much sticks, and so it gives you an idea for your site how sticky your oil will be to that material. So in summary, again, good contact equals good treatment. Just because, though, you have contact doesn't mean you're going to get that treatment or that it's going to happen immediately. But the key, what is absolutely necessary is you can't have treatment without contact. So you must have that to occur. You must have all ingredients in one location. To improve your contact, you can inject more water, or you can inject more oil. So you do have some control over that contact. It just could potentially cost you more money. And so that's where this design tool can help. Design tool is available to allow easy analysis of trade-offs. So what do you give, what do you take? Water and oil volumes, do you change your well spacing, do you change your contact efficiency, and what are your capital and life cycle costs, and how do they compare under different designs setups? And then lastly, I want to re-emphasize this point, is that the maximum oil retention is a important parameter. If you guess low, you get poor performance. If you guess high, you're going to waste money. So it is important wherever possible to measure your ORM, and it certainly helps. I know the folks at EOS, if you have that number in hand, you can help with your final amount of substrate that you need for your site. So if at all possible, come with that number in hand.
All right, well, thank you, Stephen. That was very informative. We'd like to thank everyone for listening, and you can find a copy of this as well as other webinars in our series by visiting the website. And if you click the login button in the upper right-hand corner, you can log in. And if you don't have a login, you can register by providing us with your company email address. If you have any questions about today's webinar or how to gain access to the tool that Stephen described, you feel free to either send me an email or give me a telephone call, and I'll be happy to help. Stephen, I'd like to once again extend my thanks to you for your time today in presenting on this topic, and we wish everyone a wonderful day. See you later.